SwayamPrabha. Digital India. Educated India.
Hello and welcome to this Manufacturing Systems Technology Part 2 Module 27. We learned about the Poisson's distribution, and then in this particular module we will be talking more about the normal distribution. So, the basic probability distribution underlying the Shewhart's control chart, as I think I had illustrated earlier, limits for variable data is the normal or Gaussian distribution. The probability density function for this distribution is given by fx equal to 1 by root of 2 pi e to the power of minus x square by 2, and a plot of this function over its full range minus infinity to plus infinity produces the famous symmetrical bell shaped distribution curve. So, it is actually a continuous curve over its full range and has a mean value around 0 and a standard deviation of about 1. Okay. So, that is how you can calculate the way that the normal distribution is spread up actually. So, almost the, so given this initial input that the mean value of this curve is 0 and standard deviation of this curve equals 1. So, almost the entire area under this curve, so something as indicated here, this is mean around 0 and there is a standard deviation associated with this curve. So, almost the entire area under this curve lies in a range minus 3 and plus 3. So, basically typically within mu plus minus 3 sigma, sigma being equal to 1 and mu is 0 in this particular case, almost you can say 99% of the values would be present. So, therefore, obviously there are standard tables to reflect these values. and area under the curve is determined by developing a z variate and then putting limits to this z variate. Typically, the z value is varying between minus 3.59 to plus 3.59, and the z is actually equal to whatever is the value of x minus mu by sigma. So, it is actually the number of times the sigma is spread around the mean. You already know that within mu plus minus 3 sigma, almost 99% of the values are present. In fact, if you just extend this from 3 to 3.59, they will cover almost 100% of the values. So, f z therefore is nothing but the area under the curve between minus infinity to this value z 1 by root of pi e to the power of minus x square by 2 dx, which was earlier the value for the probability distribution function of normal distribution. So, this is whatever common knowledge is needed about this normal distribution, and so obviously, if I can, the idea is that I can scale down any set of observations to this normal distribution, then the occurrence of an event within the area under the curve becomes very, very easy, which is actually important for statistical quality control. So, we would like to sort of go ahead and try to see what is the derivation of this normal distribution curve or normal curve as a limit to the binomial distribution, same way as we did Poisson's. As n is increased indefinitely, the greater the value of n, the better the estimate of the area that can be made from the normal curve area table. And one important, very important point is that this distribution is actually a symmetrical distribution. Okay. So, binomial distribution becomes symmetric only in a special case where you have exactly a probability of 50% to be fraction defective or fraction good. So, for a given value of n, normal curve is able to predict accurately the binomial distribution of a p value close to half, okay, but it does not mean that it cannot. So, that is how the limit of this particular thing can be determined. So, in light of this, as we know that for a binomial distribution, the average value mu p, if I were to look at the binomial distribution, is given by n p as proved earlier, and the standard deviation was given by n times of p times of 1 minus p, where p was the fraction defective or fraction good, 1 minus p was the fraction good. So, we want to substitute these values in the z variate. So, the z earlier from this normal distribution was x minus mu by sigma. So, how many times the x is spread from the mu value or the mean value of the distribution in terms of number of sigmas. So, I just simply substitute these values from the binomial. So, x minus n p divided by root of n p times of 1 minus p. So, although we can try to calculate a z variate in this manner, but one problem which comes or one problem which remains in relating the mathematical form of the normal curve which is a continuous distribution and the binomial distribution which is a discrete distribution function, and so therefore, how to sort of correlate a continuous to a discrete is a major question that is being asked. So, just by putting or substituting the mu p value does not help us much, because the z variate is a continuous domain variate, whereas binomial distribution is normally for discrete functions. You have a discrete value of p and you have counts 1, 2, 3, 4, so on so forth. So, there are completely discretized distribution. So, given some discrete value r, where r is the number of times rejection happens probably, the binomial formula predicts the probability of this r to occur as NCR p to the power of r 1 minus p to the power of n minus r, and this has some finite value. So, how do we predict this particular probability function with normal distribution? So, typically the idea is that when you have a fit to this normal distribution function and you are looking at the probability of a value z, so basically try to look around this value, and since in this case the z variate is nothing but x minus mu by sigma, and if it is a continuous variable, then we have no problem, because there would exist something in the near vicinity of x plus and x minus, where there would still be existing a value. But in this case, if I wanted to force fit a binomial distribution where this z is made up of r minus mu by sigma, really where r is basically the number of rejects. So, around this value r there are as such no other continuous domain values on both sides, and everything is discretized. So, corresponding to r1 let us say and corresponding to r2, you have two different discrete values. So, the area under in this particular case at a certain level of let us say z value is really not calculable unless you make certain corrections and try to use the approximation method. So, an approximation method is used to make a, you can say this can be called as a continuity correction, and we use the area under the normal curve from r minus half to r plus half, so that this way I can try to establish values near this r, which is exactly the number of times you are doing the trials, etc. Okay, so it is a discrete value. So, around this r I am establishing a domain, so that you have a local continuity at r to find out the probability of binomial at z equal to r. I am going to be more clearly representing it when we actually come to discussing a numerical problem, but here the idea would be that you will be trying to establish the z variate functions as two variables rather than one single variable at r. In one case you will try to associate z r minus n p minus 0.5 divided by root of n p times of 1 minus p, and in the other case you will try to associate r minus n p plus 0.5 divided by root of n p into 1 minus p in a manner so that the probability corresponding to a z equal to r can be found out as the difference in the regions between z1 variate and z2 variate 1 by 2 pi root e to the power of minus x square by 2 dx, which in any event is the cumulative area. So, this is basically a case where you are assuming a z variate corresponding to r minus half. So, let us write this down as z variate corresponding to r minus half, another z variate corresponding to r plus half, let us call this z1 and this z2. You are basically trying to find out the area under the curve up to the point z1 and delete or deduct the area up to the point z2 to find a local probability in that particular domain. So, you are trying to force fit this into a local continuity, so that the values can be calculated in accordance to what is there in the normal distribution or normal curve. So, I would like to discuss a small example problem here. So, let us say samples of 45 are being taken from a stream of products this product is on the average 25% non-conforming. So, the p value here is 25 by 100 or 0.25. So, about a fourth of the product fails normally to conform to a certain specification. So, we would like to find out the probability that a sample of 45 will contain 13 non-conforming items. So, the first goal here is to represent this by a binomial distribution. So, we will calculate using a binomial distribution. So, let us say n equal to 45 and the probability of acceptance or rejection here is about 25%, a quarter of the products are rejected. R here is 13. So, obviously, the probability of having exactly R rejects in the sample of 45 is given by 45 C 13 p to the power of R. So, p to the power of 13 times of 1 minus p to the power of 45 minus 13 in the binomial manner, and this can be, this is coming out to be 0.1093. If you were to use the normal distribution to calculate the same thing, so therefore, the probability is about 11% or maybe 10.93% if you do it with the binomial distribution. While using normal distribution, we will again use the similar kind of limits as talked about by making a local continuity. So, we want to create two variates z1 and z2 here, where z1 is basically 13, that is the R value minus NP. So, obviously, NP in this particular case, because the sample size is 45 and it is about a quarter reject, is about close to 11.25, and similarly the sigma p from the normal distribution here is root of NP times of 1 minus p. So, this comes out to be equal to 2.905 when you calculate substituting the p value and n value as 1/4 and 25 45 respectively. So, here we can calculate this as r minus np, that is minus 11.25 minus of 0.5, making a local continuity around the value r, divided by 2.905, it comes out to be 0.4303. Similarly, a Z2 variate here would be in terms of 13 minus 11.25 in the plus side of the r, we make a local continuity by putting r plus 5 or r plus 0.5. So, this divided by 2.905, which is actually 0.7745. So, the probability of having exactly 13 rejects here in this case would actually be the area under the curve up to the point Z2. So, let us say I just call it the probability distribution function or cumulative distribution function CDF of Z2 minus of CDF of Z1, and from the normal tables these values can be obtained as 0.7807 minus 0.6665 corresponding to this Z2 and Z1 value, and this comes out to be equal to about 0.1142. So, in this case with the normal distribution and assuming a local continuity, you are fairly close, you are getting about 11.42%, okay, which is very close to the value expressed earlier as about 10.93%. So, you see that it does not give much impact if you make a local continuity around the discretized value of r, so that you can implement the normal distribution function suitably. So, in this whole module we have sort of analyzed various things related to the Poisson's distribution, how that can be fitted, and also the normal distribution and how these can be aligned to the binomial distribution. And binomial distribution earlier has been given summarily in a very nice manner as to how this can be aligned to acceptance sampling plans. So, obviously all these things fall in line that all these three distributions can be used appropriately and efficiently as the case may suggest. For example, in Poisson's case it is a case of large samples with very small probability, okay, or in this case normal distribution case, it is just to simplify the calculations that would otherwise generate out of binomial, you are making a local continuity, so that the normal can be force fit to the binomial. The idea is in all this manner you can predict the probability of occurrence of a certain number of rejects, which is very important. So, the only other thing that I would like to share now is what are the real values which are plotted in tables which approximates both the Poisson's and the normal distribution case. If you may recall, the Poisson's probability distribution had a cumulative density function CDF, which was provided by the probability of the value r to be less than or equal to some value c given a certain mu c rate of occurrence, okay, which is the average, and which was represented as sigma r varying between 0 and c mu c to the power of r e to the power of minus mu c by factorial r. So, having said this, as the probability of having exactly rejects less than equal to c and for a particular mu c case or a particular mu n p or whatever you can call the mean of the distribution, the table G here shows the summation of these terms, which is Poisson's sort of exponential binomial limit. So, this table G is basically 1000 times the probability that is being reflected here. So, 980 exactly means 0.98, okay, of c or less occurrences of event that has an average occurrence which is given equal to mu c or mu n p. And so, if you see, if the mu c value right about here is let us say 0.02 and the number of occurrences are exactly 0 times or 1 time, the probability is 0.98 and 1 respectively. Similarly, if the mu c is around 0.95 and the occurrences are exactly let us say 1 time, so corresponding to 0.95 and number of occurrences equal to 1 or less, the total cumulative distribution is 0.754. So, this is how you read this table G, and you can actually apply Poisson's case to find out what is the probability of occurrence of a certain event, okay, in the whole distribution. So, that is how you can sum. So, these are tables, and these tables, as you can see, correspond to a mu c value from 0.02 all the way to almost about 22 or 25 or so, and the c value varies all the way from 0 to about 43. Obviously, as you know, there are certain terms which are redundant. So, for example, for a case of 10.5 mu c, if I go above 23, the probability is all going to be 1. So, we have just made that redundant. So, whenever there is a limit to the full probability of 1, you sort of do not repeat the values here and truncate the table in this manner. So, this right here is up to 43 occurrences, that means for 43 or less c values, you can plot or you can read from this table all mu all the way about 25 or so. So, that is how these calculations have been performed. You can keep on changing and increasing this table by looking at the distribution function, the cumulative distribution function that has been given to you earlier and discussed in some details. Okay, but the idea is that this is the way to apply the Poissons to calculate probability of occurrence of some particular event in such complex distributions where the probability percentage is very low and the numbers which are involved or the number of data sets are very large. Similarly, as I think mentioned about the normal tables, this right here shows the area under the normal curve corresponding to a certain z variate. The z variate again varies between minus 3.5 to almost about positive 3.5. Obviously, this means to accommodate almost 99.99% values of the occurrences, and this corresponds again to a z value of all the way from 0.00 to 0.09 so on so forth as given in table A. So, you can use these tables for the purpose of you can again have a look at this. This is part A of the table, again part B of the table in a similar manner to like just as in the case of Poissons, and you can use these values for, and these are available in any other source including even online. So, you can look at these values and try to estimate the probability of occurrence of a certain event R. For example, R could be the number of draws in as we just executed earlier in case of defining the binomial distribution. So, that is how you calculate using the normal tables. The advantage here is that the calculation becomes much more simplified in this particular case, just because you are force fitting a function which is having a which is centered about 0 and has a standard deviation of plus or minus 1. Okay. So, it becomes lot more easier to handle this way numerically. So, having said that, I would like to close this module here, and in the next module we would start to plot at least some of these acceptance sampling plans and how P charts can be used to govern such plotting and what could be the interpretations coming out of the system. So, as of now, thank you so much.